Alrighty, so we're talking about rotational inertia as we rotate through a central axis. So we're thinking about a lot about the center of mass, but then we offset it. So if something is spinning from the center of mass, let's say we've got this heavy object and this light object. I could spin from the center of mass, which should be closer to the heavier object than the light object. But also, I don't need to do that. What if I wanted to spin it from the center? I still could grab it from the center and twirl it from the center. Okay? So, right here, the scenario, a mass 3m and a mass m are attached to a connecting rod of negligible mass, and their center of mass are separated by a distance 8L, as pictured to the right. So we have a point mass here, point mass here. We're going to spin it, and we're probably going to find the center of mass to pivot it from. So relative to 3m, where on the connecting rod is the center of mass, xcm, located? Back in the day, we learned that our xcm formula should work, that we need to figure out the scale of it. So m1x1, right? Plus m2x2 divided by, we want x out of here, so we're going to say we're going to divide out the total mass. That should give us the center of mass, right? For 2 points of an object. I'm going to flip these around because it's bugging me. I just wrote it before I said it. M1, X1, M2, X2. Alrighty, so if I've got these given factors, what's my first mass? 3 big M, right? What's my distance from our point? We could call this 0L, right? Along the 8L number line. This would be at 0L. Plus, this will be just M. And it's 8L away. And my total mass is 3M plus 1M. So I've got 8ml over 4m. And our answer is 2L away. That makes sense, right? Because I already drew it there. If this is 4L away, and this is 1L, 2L, 3L, 4L. So it also makes sense because I would be 3 times closer to the 3m and 1 times the distance away from the towards this. So it's proportionate. Makes sense because it's chopped up nice evenly into 8s and there's 4m total. Assume there is a rotational axis at the center of mass. So now we're pivoting it from here, just like in our labs where we had a pivot point and it can rotate from there. If it is allowed to spin from there, what is the rotational inertia? And so inertia, we're talking about point masses. For any case, it would be the sum of mr squareds. And because there's 2 points, we can just say m1r1 squared plus m2r2 squared. That's the easiest way to decide it. If we're pivoting from here, how far is the 3m? It's 2L away. So my 3m, 2L squared, plus 1m. How far is my 1m from that pivot point? 6L squared. 2 times 2 is 4? Yeah, 4. Okay, I don't know why I questioned it like that. 3 times 4 is 12. So we've got 12ml squared plus 6 times 6, 36ml squared. I won't question it this time. What is 12 plus 36? I mean, unless you got it wrong. All right, 48 ml squared. And that's if I rotated it from this pivot point. What's interesting about this pivot point is that it would feel balanced. What contributes more to the fact that it's hard to rotate or easy to rotate? What contributes more to how difficult it is to rotate? The right-hand side or the left-hand side? The right-hand side? No, the left-hand side or the right-hand side? The right-hand side contributes more to how hard it is to rotate, but it will feel balanced as you spin it because the amount you have to torque is the same. Why? What is the torque equation? Torque equals force times radius, whereas if we're spinning it along a line, whereas right now we're talking about just how hard is it to rotate, which is r squared. That r squared means we're talking about r times r. What is this? I. Okay. So even though it contributes more to it not wanting to rotate, each side is just as easy to rotate, interestingly enough. And that's based off of the radius that we are away. If that's confusing, remember I had those two rulers where I had the weights in close and then the weights out far. And even though they had the same weight, this was just stiffer to rotate from the center point. Okay. Number 3, it says a new rotational inertia of the system if it rotates around a parallel axis at distance L to the left. That's a convoluted way of saying, hey, look, just move 1 L over this way. Okay. If we change our pivot point, so in the first one, we're pivoting from here. In the second one, we're going to pivot from a little bit over to the left instead. We're going to move 1 unit in our big picture this way. So our green arrow where we're pivoting from and turning from is slightly different. How would we end up doing that? All right, so let's set up our equation. We've got the same facts. We've got I equals, is that legible? Is that visible? I'm going to switch back to a darker color. Even though I would like to color code it, I'm not going to be able to. I is equal to the sum of the mr squareds. I is equal to the sum of the mr squareds, which means I've just got the same 2-point masses, m1r1 squared plus m2r2 squared. What's convenient about this is that my m is still the same. What is this? 3 m's? 3 m's. How far am I from that new pivot point, though? Just 1 L squared away. So L squared. M2 is just 1 M. What am I going to plug in for R2? 7 L squared. So I've got 3 ML squared plus 49 ML squared. Double check. Do you see where I got the 3 from? Do you see where I got the 49 from? 7 squared. 50. No, not 51, but 50. 52. 3 plus 49, 2 odd numbers, gives me an even number. That's my quick check. ML squared. Bigger or smaller than when we spun it from the center of mass? Bigger. I mean, it makes sense that it should be the easiest to spin it from the center of mass, right? Okay, so we're going to make sure that that's true. It should be the easiest to spin it from the center of mass. So let's find that out. We're going to move it the other way now. So if I were to color code it, I'd probably put a new pivot point in here, and then I draw it up top. I'm not able to get that in scope on the page at the same time. I guess I could show you, though. I'm putting this light blue pivot point at here for part 4. All right. So that light blue tells me that I am, same thing, m1r1 squared plus m2r2 squared, that I'm going to say 3m and 1m. But what's my distances? I'm 3L squared plus 5? Yeah, that makes 8. 5L squared. 3 times 3 is? Times another 3 is? So I've got 27ml squared. And I've got 25ml squared. Right? 5 squared. Is 52ml squared. Interesting. Yeah, if you compared the answers to number 3 and number 4, they're the same. That's what we're going to write down here. Where is the rotational inertia of the system the lowest? Probably the center of mass. And if I move 1 meter or 1 unit to the left, or I move 1 unit to the right, if I move equal distances, it's the same. Like in number 3 versus number 4. That's not a 4. Why did I put a V? That's weird. It's not even the Roman numeral for it. Number 5. Number 5 says, what is the new rotation if I start on the heavy end? So now I'm pivoting from this point right there so add that to my key. If you were to ever grab my notes, that would make sense. But right here, and that should be pretty easy because like my center of mass, I've got 3m but 0l squared plus 1m and 8l squared. And we find out that we're at 64 ml squared. 0 plus 64 ml squared. So, as we get further and further from the center of mass, does that help us spin or make it harder to spin? Makes it harder to spin. And not only does it make it harder to spin, but as I move away, I bet you if I moved towards the center, 2 meters to the other side, it'd also be 64. You could try that if you wanted to later. We need to keep moving forward, though, for the sake of being tidy and quick with our notes. We've got this whole page about parallel axis theorem that says if we start to offset, it is the same thing as if we were to. So if we were to offset my new inertial value, how hard it is to spin, would equal the easiest inertial value at the center of mass plus m of the system times h squared. I went ahead and wrote m of the system with subscript here. What the m is the total mass of the rigid body system. I don't know why I was about to write 3 S's. Mass. And then the h is the offset distance, right? So that would be the distance between the axis through the center of mass and what we would call the parallel axis. Okay. So the distance between the center of mass and where we're choosing to spin it from. That's the code for what parallel axis means. Okay. So it's the offset distance. That's an easier way of saying it. A lot of times you won't see this cis right here. It'll just be mh squared. Okay, I just want you to know it's the full mass of the whole system. I'm going to move this a little closer, tighter in, so it looks like mh squared. Alrighty, so could we use this new formula to solve 3 and 4? What does that look like? Well, the ICM we found in problem 2. ICM, when I spun it from the center of mass, would be the same as that, what is it, 48? That's the lowest number. 48 mLs squared. But then, what was the total mass of the system? 4 m's. And if I were to offset it by 1, my H equals 1L in both 3 and 4, right? Plus or minus 1. And I'm looking for my new I. We can use our formula. I equals ICM plus MH squared. ICM was 48 ml squared plus 4 m's times 1L squared. So that's how we got to 52. It was just the amount of masses we were off by the L squareds that we were off, but 1 squared is just 1. We could try that with number 5 as well. We're offsetting by 2 L's, the same 4m. What's 2 squared? 4, and 4 times 4 is 16. So when we flip back, is 64 mLs just 48 plus 16? 48 plus 16 is 64. And so our formula to offset works. Now, you're like, Mr. Kwan, it's pretty easy with point masses just to add up all our problems. Okay? So then we gave you a problem specifically where we need to use this formula. Because this formula is actually made to simplify our lives in many cases. And so it's actually a very convenient formula. I've got an earring here. The earring center is here, but it's not going to spin from here. If I were to see this at some time later, I could rotate it, but it's going to be rotating by where it's pinned into the ear. Does that make sense? If you try to rotate this from the center, you're going to drag the pin, which is attached to the ear, and you're going to drag the ear down lower, or you're going to break skin, right? So that doesn't sound very good, okay? So we're going to rotate from the pivot point right here. I'm going to put a P right there for pivot point. That makes sense. And it's offset to the very far edge. So here's my question. What is the I value for a disk or a cylinder? Okay, so if I have 1/2 mr squared, that's pretty convenient for a disk. And not just that, but if I were to worry about not so much the mass of the disk, that's just going to be the mass of the disk. The H value that I need is going to be R. Yeah, it's the radius. It's how far we're offset by. This pivot point is one of the radiuses away from the center. And so my equation is I equals ICM plus MH squared. My ICM of this disk is 1/2 mr squared, but my offset is mr squared. Right? Mass of the disk is offset of the whole system. The mass of the whole system is just the disk. And I'm offset by the radius because I'm spinning it from the edge of the radius. This is 2/2 plus 1/2 is 3/2. My new I value is 3/2 mr squared. You see how convenient that formula was? And there was no point mass to add. We have a disk. And conveniently, we have a disk offset by some geometry. Okay? So when is using the parallel axis theorem a better strategy than adding the rotational inertias? I mean, when it's not, it's... So I would say when ICM is known, relatively known, I mean, I had an equation for it. It wasn't exactly like I know it's 22 or 83, but it's known in terms of our variables. And or this adding all of the i's is just not practical. Not practical. Yesterday, when we were talking about adding these 3 points, they both had a mass of 2 kilograms, 2 kilograms, both. All three of them had a mass of 2 kilograms, 2 kilograms, 2 kilograms. That was very convenient to add them together, right? Summing the amounts is not too bad. But in this disk, there's just one item, but it's not practical because we are offset. So when ICM is known and the summing is not practical, when is it better to go back to adding and finding the sum of the I classically? When point masses are easy to determine. Okay. So there are times when we are able to sum up all the individual I values easier than doing this. And it's pretty... I feel like that will come to be obvious as we start practicing them.